the goal is basically to derive the heat flow equation, and the heat flow equation is like we would have then the rod and we keep heating it, and then we look basically how the temperature evolves in such a rod, for example. We see that for us, especially in geophysics, it's important to understand that heat dissipates by conduction. In this case, for a solid, basically. It's not by convection. So if we would have, let's say, put cold milk into a hot coffee, then you would have convection, basically, which is also a heat transport. But for us, what we want to mostly come to is basically the conduction of heat, less the convection of heat. Another way of transporting energy and heat would be, for example, by radiation. So a hot body radiates basically energy or heat as well, which we also don't want to go into. For us, it's the most important mechanism is this conduction of heat. Okay. That leads then to the heat diffusion equation. But let's start with energy first. And again, we define our little volume, little body, with the volume Vt. This volume has these little volume partials, dV. And then this body or this material is characterized by having a velocity v and a density rho. So the body can move, it can even move in different directions if it's an elastic body, etc. So that's the velocity field v, basically. And then we also have the surface here of the body, which we denote as sigma. And T always means it's time dependent, so the body can change its shape. So energy, let's look a bit at the different energies that we have. And the first one is kinetic energy. You probably know from classic physics how you define kinetic energy. Let's say E, kinetic.
1 divided by 2, mass times velocity squared.
Exactly. So that's the classic formulation for kinetic square, for kinetic energy. So in our case here with the volume, we define it as a volume integral, so it's not mass, but we write it in terms of density. So for us then the kinetic energy of this volume, of this body, the volume Vt, is this integral of density. So you can think of this as the mass. Now times the velocity square, and here we just take the dot product of V times V. And then integrate over the volume. So that's how we would define kinetic energy here now in this continuum mechanics formulation. Good, and then what we're interested in is the rate of change of kinetic energy. So again, the rate of change, rate of change. And the time derivative of this quantity, of the kinetic energy. I'll take here the 1/2 inside. Good. We saw rate of change of mass, rate of change of momentum, rate of change of kinetic energy is exactly the same as the time derivative of the kinetic energy. Now, when we look at energy, we also have to look at, for example, how mechanical energy is added to it. And by mechanical energy, I mean the work that is done by the forces that are applied to that body. I'm not sure if you remember what work is defined in physical terms. So work, classic physics, is force times
displacement.
Displacement, yes. So that would be a classical definition of work. Now, if you think of what would be the rate of work, like the rate of change, so that how much work changes, you can think of taking the time derivative of displacement, which becomes then velocity. So it would be the force times velocity. This would be a rate of work which is applied. Good, let's write this down in terms of our continuum mechanics formulations. So what we're interested in is the rate at which mechanical energy is added. And so again, we basically have both type of forces that we saw yesterday as well. We separate into body forces and forces which only act at the surface. So the tractions basically, or the stresses that are applied at the surface of this volume. So if you look at the rate of work at the body forces, it's basically our integral Vt. Now the velocity times the body force, vector F integrated. So this is basically the rate of work by volume forces, or body forces. Let's call them body forces like last time. Good. And then again, the surface. So the tractions basically, and here we just have V times small t, and small t is the traction. Oops. So this is the rate of work by surface traction. Tractions. If you remember tractions, traction small t is defined as the normal of the surface dotted with the stress tensor. So we saw that as well yesterday. Good. Now let's come to additional energies. What kind of energies you can still think of that we need to account for? So one thing is we had kinetic energy. From classical physics, you know there's a second energy which also belongs into that category. There's kinetic and potential energy. And then if we think of the Earth, what produces heat in the Earth?
nuclear reactions?
Yes, radioactive elements. They are also a source of heat. So there is a heat production due to radioactive elements. So these two we want to basically add as well now. So these two additional energies. Good. So let's quickly write these down, these two energies. And potential energy, if you think of this body, is basically the thermodynamic internal energy. Think of it as measuring like the temperature of this body, of this element, which is basically then a measurement leading to the internal energy of the body. This is like the potential energy equivalent. So we have the thermodynamic, internal energy, and the heat production. Which in the Earth is due to radioactivity, the radioactive heat production. Good, and what we are interested in is again at the rate of change, basically, of these energies, or the rate at which they are producing heat, for example. So let's write this down. So what we're interested in is the rate of change. The first one, the thermodynamic, internal energy. And we write this as the dt of the volume integral of rho, and for internal energy, we just use a capital U. dV. So let's use this capital U as internal energy. And you see we write it inside this volume integral, so it's basically internal energy per unit mass. Good. So if you want to think of an ideal gas, in an ideal gas, U, the internal energy, basically related to the mass times the temperature of the gas. And we come later to that part for the internal energy. So we need then somehow a formulation that relates internal energy U to, for example, the gradient of the body. And this will be then again a constitutive relationship that we will need to solve the heat equation. So for now, let's use the internal energy U. And then for the heat production, here again, let's look at the rate of heat which is produced. So the rate of heat production. Which in the Earth is due to radioactive decay, radioactive elements. So we can again use an integral formulation with rho times h, small h. And here small h would be our heat production rate. And when we write it in this integral form, especially again per unit mass. Good. Now we're almost done actually. We have almost listed everything about energy. Something we are still missing is how much heat is lost through the surface, basically, through conduction. So it's the heat flux, basically, that we need to have as a final term. So let's look at that rate. At which heat is conducted out. Of our volume. And so that would be now a surface integral going out of the surface. Normal dotted with this capital H vector, and the capital H is the heat flux. So think of a surface, and then we have a heat flux that goes out of that, transports heat away. Good. Now we have all our rate of changes of energies that are involved. So for the conservation of energy now we put all these terms together. So let's write that down. Let's write down the conservation of energy. And let's already put a bit the terms together that we have. So let's start with the kinetic energy. This 1/2 rho V times V. And then we see we also add the potential energy, or in this case, the thermodynamic internal energy. So we have kinetic plus potential energy basically on one side. So if you look on top, we have the rate of change of thermodynamic internal energy is dO dt, volume integral of rho times U. So let's add that rho U term. And then this is dV integrated. Okay, that's our left side. So it's basically kinetic and say potential. Or if you prefer, internal energy. Which is now equals to the mechanical energies plus the heat production is left and the flux, basically. So let's put these terms also together. So we have the volume integrals, and then we have mechanical energy from the body forces, F. Then we have another volume integral you see for the heat production. So So let's put this inside as well, and yeah, let's say rho h here. This is dv. And now have the surface integral added plus the surface integral. Which ones we have? Well, we have the heat flux, the surface integral, and we have here the rate of work by the surface tractions, also surface integral. So let's write that down. So for the tractions, we would have, if you look here, V times the traction, but the traction we can write as in form of the stress tensor. Let's just do that as well. So then we have n dotted with the stress tensor times the velocity. And we have this heat which is transported out. So we put a minus in front of the heat flux and times h. Okay. So that's basically our equation for the conservation of energy. So the rate of change of energy. On the left-hand side, you see kinetic and internal energy. The rate at which it changes is equal to the rate at which mechanical energy is added to the system, plus the heat production, minus the heat flux, which is transporting heat out of the system. That's basically our energy balance that we have. Good. So by now, probably you see what we're going to do. Instead of having this surface integral, we want to have a volume integral. For that, again, we apply Gauss theorem. So these quantities you see inside the surface integral become then, take the divergence of these quantities and can write them as a volume integral. So then everything is under a volume integral, which simplifies then the lives, because it's then valid for any volume again. So we can look at the quantities under the integral especially. So let's do that here. Let's put everything under a volume integral. So the top one is that stays the same. We have the rate of work of body forces plus the heat production, rho h. And now we have this divergence of the stress tensor times V minus the heat flux h dV. So that's just by applying Gauss theorem. So we take the divergence of these quantities, and this is now valid for any volume Vt. Good. So let's write it down without these integrals. And to do so, what we would do is, for example, we rewrite. So after some more math, or after some math, we will find, so something that we were going to use is basically the divergence of an expression like this of the stress tensor here. We're going to rewrite this bit. So we have a term V dotted with the divergence of the stress, plus a term where we have the stress tensor tau dotted with grad V, for example. So let's write it down a bit, what we would have. So we would have here rho, and now basically we take the material derivative of 1/2 V dot V plus U, then plus the divergence H minus the stress dotted with V equal to V times the body force plus, now instead of rho H, we just write H with a tilde on top. And here, H now is the heat production, but it's not the heat production per unit mass, but here it's per unit volume. So we can omit the rho basically that we had. So that makes things a bit simpler. So now it's just the heat production per unit volume. So we rewrite these terms on the left-hand side a bit more. Let's see. We have then V rho dual derivative of V minus the divergence of the stress minus body force plus F rho the material derivative of the internal energy U plus the divergence of the heat flux. Now I'm going to have a problem with this guy here. Let's see if I can move it down. Good. So this is now equal. What is left is basically we have the stress tensor with the grad V plus our H projection. Good. Why do we write it now in this way? It's because of this term here. So if you have your notes for the conservation of momentum we saw yesterday, this should look familiar. So look it up and what you see, oh, okay. This is conservation of momentum or linear momentum. And what it means, it cancels out basically. So then things get a bit more simpler. And what we want to use as well, if you look at the right-hand side with this double dot product of these two tensors, so it's the stress tensor double dot product with grad V, which is also a tensor. So it's a double dot product between two tensors. If you write it down in index notation, it will be Tij times grad I Vj. And again, you see repeated indices, so that means basically we would have to sum over these for I and j. But we can write this basically also in a form where we have the 1/2 grad I Vj plus grad j Vi, which looks pretty much like the stress tensor double dotted with the strain tensor. But the strain tensor is defined in terms of displacement and not velocity. So since we have here velocities, it's not the strain.
Strain rate.
But it's the strain rate, yes. So for that, we have this dot on top of strain, the time derivative basically of strain, so the strain rate. So this is strain rate. So let's write it with this strain rate, then we find so rho, the derivative of the internal energy U, the divergence of the heat flux, this term is equal. Now we have the stress tensor double dotted with the strain rate. Plus our little h tilde, our heat production rate. And that's it. So that equation is conservation of energy. Good. So something we can look at for elasticity particular is a little side note that we put here. So a little note here on the conservation of energy. So due to the conservation of energy, you see that for an elastic medium, where we have the stress tensor related to the strain by the elastic tensor C. That is Hooke's law for an elastic medium. You see that stress relates to strain linearly by the elastic tensor. And so if we look at the conservation of energy for such a medium, we see that we would have rho Tu equal to the stress tensor dotted with strain rate, which then basically can be written with Hooke's law as strain times the elastic tensor dotted with strain rate here. So this is our stress, which is now related by Hooke's law to strain and the elastic tensor. And so in the absence of the heat production, so assuming there is no heat production and assuming there is no heat flux out of the medium, that from this expression, obviously it follows that C must have symmetries. So you see strain rate is defined such that it's a symmetric quantity. Strain is symmetric. And so C has to be symmetric as well. And the symmetry that follows from this for the elastic tensor is that CijKL has to be equal to CKLij. So this symmetry of the elastic tensor is due to the conservation of energy. We will see that when we look at the conservation of angular momentum, there's an additional symmetry imposed on the elastic tensor C. So that is the reason why the elastic tensor shrinks down from, 81 free parameters down to 21. So one symmetry follows out of the conservation of energy. The other one we will see in the next lectures when we look at the conservation of angular momentum, that there is an additional symmetry for the elastic tensor. Good. Do you have some questions right now? What we want to do is basically, let's look now at the heat equation. Let's use the conservation of energy, the equation we set here on top, and come to the heat equation. Good so far?
Yeah.
Okay. So let's come to the heat equation, and here especially we have to look into this internal energy U. So U is a thermodynamic quantity. Which needs an equation of state. To relate it to temperature. So U as a function of temperature. And now above I use T for stress, the stress tensor. So I use here T with a hat for temperature. Maybe I should use some other fancy symbol, but let's just use the T with a hat as temperature. So that's an equation of state. And what we are interested in is basically the rate of change of U. So material derivative of U, which is basically the derivative of U with respect to temperature times dt, the derivative of the temperature. And so this quantity here, the derivative of the internal energy with respect to temperature, this is called the specific heat. So it's the specific heat coefficient, in this case at constant volume. Good, so let's use that now basically. So now we have this constitutive relationship, if you want, of the internal energy with temperature. So we can use that, and then we also need something that relates the heat flow, our heat flux H, with temperature. That's the constitutive relationship as well. So what we assume basically is that heat flux now our H, capital H, the heat flux, is proportional to the temperature gradient. So grad of T hat. So if we have a temperature gradient in this rod, let's say on one side it's hot, the other side is cold, then heat flows in the opposite direction. The gradient of temperature would be positive, but heat flows then from the hot side down to the cold side. So it's basically in the negative, the opposite direction, the gradient. And this is Fourier's law, basically. So that is Fourier's law. Similar like we saw Hooke's law, which is a constitutive relation between stress and strain. We have Fourier's law, which is a constitutive relation between the heat flux and the temperature. So Fourier's law states basically that heat flux H is opposite to the gradient of the temperature times a factor, and it's linearly related by, let's say, kappa. Where kappa is the conductivity of the material. So we can write our conservation of energy as rho, now the specific heat times material derivative of temperature. So using the equation of state, the rate of change of internal energy. Then we would have the divergence of the heat flux, which using Fourier's law, this constitutive relation, is being minus kappa times the gradient of temperature. Is equal to the heat production. And then writing that, we are basically ignoring now that for a solid, heat flow is by conduction and not by convection anymore. So that's why we use Fourier's law here. Fourier's law relates it for heat conduction. So we have only conductivity, which is important. If we would have a fluid where we also have convection, then the heat flux would also have convective terms, for example. And if we would even include radiation, then it would also have a radiative term, which then relates the heat flux to all these additional terms. For us, when we look at the solid, heat flux is driven by conduction. There's no convection, and we ignore the radiative part. So that's why we can just use Fourier's law, which relates heat flux to the temperature gradient in a linear way, basically, using the conductivity. Good. If you compare from a top here, we ignore the stresses and the strain rates. So assuming that we don't have these stresses acting, and we are only interested in like having this rod and heating it in the middle, and there is no stress acting on the volume that we need to consider. So all we need to look at is basically the internal energy, the conduction of heat, and the heat production in this rod. That's the heat equation we have here. So we can also rewrite it a little bit, putting terms together. So the specific heat. Now instead of the material derivative, we use again the Eulerian framework. So we have the time derivative of temperature plus this term with V. Of grad temperature equal to the divergence here of kappa times grad temperature plus the heat production. And so this is written now in Eulerian framework, and this again is the heat equation. So think of H as being a heat source. Oops. Okay, good. Is it back? H as being a heat source. Density and specific heat you can think of being material constants. If you also want, for example, for an ideal gas, etc. Well, let's just keep it that way. So it's given by the material properties, rho and theory. The main point here is if you look at the equation, the only unknown is temperature. So the heat equation, when we solve it, we solve basically for the temperature field. Good, how would that look in 1D? Because the 1D equation is the one we're going to solve then numerically with our methods. So let's write that quickly down, the 1D equation. So we find that we have rho CV, the derivative of temperature with time, is equal then to the derivative of space, the conductivity times, again, space derivative of temperature, plus H. So this is the 1D heat equation, basically. Or if you like, is the heat diffusion equation, because diffusion is the main process by which heat or temperature is transported. Good, so this is the heat equation. Let me just quickly put down the wave equation as well, so you can compare it. And the wave equation, we didn't use U, we used S for displacement. Looked like that. So if you look at these two equations, they look very similar. The only main difference you see is the time derivative, where for the heat equation is first order, for the wave equation is second order. And so when we solve these two equations, we pretty much see how these equations can be solved numerically. And you can think of these two equations being like proxies for any sort of equation you will encounter in geophysics. So that's why we focus on these two equations. They give us the main characteristics of almost any equation in geophysics. So once we can solve these two equations, then we can pretty much solve everything in geophysics. Good. So that leaves the mathematical part, let's say. And then what I would do is look into the homeworks. Is that okay? So if you have questions on this part, so everything is clear. So we started with basically listing all types of energies: kinetic, potential or internal energy, mechanical energies that are added to the system, plus heat production. For the Earth is radioactive heat production. And then we put all these energies basically together into the balance, to the conservation of energy, where we looked at the rate of change. So energy changes only by adding mechanical energy, for example, or adding heat production, or through heat flux. And then it's a bit of math that we go through, but we see that the conservation of momentum can help us to simplify terms a bit. And we end up with this basic equation for the conservation of energy. Out from that, we already see that for an elastic medium, there is this symmetry in the elastic tensor that is due to the conservation of energy. And then if we further include an equation of state for the internal energy, which relates it to temperature, plus Fourier's law, which relates the heat flux to temperature, we actually end up now with an equation that we can solve. So this one we can solve for the temperature field T. And think of the temperature field T as being a function of position and time. So if we write down the heat equation in 1D, we see that's basically the 1D equation, heat diffusion equation, if you want. Has a first order time derivative and first order spatial derivatives. And you see if the conductivity is constant, if it doesn't change in the medium, it could be taken here out, and we would have then a second order spatial derivative, temperature. And that's what we're going to look at for the homework. We first simplify, but then if you want to allow for a general expression of the conductivity, if you allow it to be different within the medium, then we have these first order derivatives. And the wave equation looks very similar. The main difference is that we have a second order time derivative of displacement. But then again, these first order spatial derivatives. Good. So let me finish here this whiteboard, and then we look a bit at the homeworks. It's good?
Yes.
So for the homework, shall we quickly look at the parallelization homeworks? I'm not done yet. I'm not done through all your reports. I saw some of them. Some used MATLAB, some used Python. So it's great. It's great the reports you sent. So I'm going through it one by one and give you feedback on these reports. What I would do is I would put like a solution folder into this Dropbox. So you put your homeworks there. And then I put into that same folder like a solution folder, and I have some solution with MPI, for example, for this Fortran, little Fortran toy example that I give you, how you would put MPI commands into it and compile it with MPI, how you would have OpenMP. I have a thread example in C. There's even an OpenCL and CUDA example, and an example with a Jupyter notebook. Let me look at that again, how we did that. Often that's basically like based on contributions earlier on from other students in this class. So every now and then I look at some of these and somebody comes up with a new solution, like a CUDA solution or OpenCL, etc. And then I put them in here. Yeah, let me look through your PDFs and reports and codes, and then give you some feedback on that. What I want to come to is basically the homework about now the heat equation. Shall we do that? So let me quickly show you the presentation, which is gone by now. Okay. How come? Ah, here it is. Good. So you see these slides? So the homework for next week will be to solve the heat equation basically with finite difference schemes. We saw the schemes yesterday. And here basically is again the heat equation. And we can put terms a little bit together. I don't know if I see, I don't have a pointer. Can I? I cannot, okay. But if you look at the heat equation, you see that when we assume that we have these constant properties, the constant thermal properties, we can write the heat equation in a very simple form. At the bottom, you have it there in the red box. So then we only end up with the time derivative of the temperature field is equal to this diffusivity coefficient D, which is a constant, times the second order spatial differentiation of the temperature field. So this is a very simple equation which gives us heat diffusion, and we cannot approximate these derivatives with the finite difference schemes. So what we play with are, for example, these different schemes, and you can choose a forward scheme in time and central difference scheme in space, for example. Then in these slides, they are already given, basically. They show you how these schemes look like. You have the forward in time, central in space, and you see the forward scheme is for the first order derivative, and the central scheme is for the second order derivative. And so then you can write these down, basically these approximation, the finite difference approximation of these differential operators, and combine them into one equation, which is given you here already. And what you see is you can put then the time at time step n plus 1 is equal to all the time steps at the previous time n. So it's an explicit formulation to go from n to n plus 1 for time, for the temperature at time n plus 1. And so this is an explicit scheme now. So for this explicit scheme, it's very simple to compute the next time step basically, because it only depends on the previous times. And this is what you implement basically, this scheme. So that's something you can implement and then solve the temperature field in space and time. Good, we can now play and say, well, instead of the forward scheme, let's use the backward scheme in time and the central difference in space. And if you do so, again, the two schemes, this time the backward scheme for the time derivative. You put this together, and now it looks like this, basically, your expressions. And you see that the temperature at time n at position I depends now as well on the temperature at time n at the same time of your neighbor I plus 1 and I minus 1. So now you're not explicit anymore, because you need to know basically at the same time your neighboring field as well. So this is called an implicit scheme now. But this can be solved as well. You put it into a matrix form, and you can solve them by inverting the matrix for the temperature field. It's one way of solving such an implicit scheme. So you can do this as well. And then see, for example, what's the difference between an explicit scheme and an implicit scheme now. So what's happening if you choose different time steps, for example? And the Crank-Nicolson is a very popular scheme in finite differences, which gives you a particular combination basically. And here you see especially the central scheme is a bit different because you evaluate it at these half points, for example. So it's a particular finite difference scheme, which is very popular. And if you are brave, you can try and implement this scheme as well, the Crank-Nicolson scheme. It's given here already, the expressions for it, how they would look like. And then once you have these matrices set up with the corresponding coefficients A, B, C, D, E, and F, then you can solve for the temperature scheme. So you can start stepping through the temperature field evolution. Good. So one of the main reasons we want to look into it is to get a feeling for explicit versus implicit schemes. And you will see that when you start them playing with the time step, suddenly one scheme, the explicit scheme, will start blowing up, basically. Have these exponential increases, numerical instabilities that start showing up when you choose a time step which becomes too big. Well, the implicit scheme always is fine. So it leads us to the stability of a scheme, the stability of an explicit and the stability of an implicit scheme. Why is one blowing up while the other is not blowing up? And that's something we will look into as well. Quickly trying to analyze the stability. And then you can also look at the Crank-Nicholson scheme and the accuracy of the scheme. So how accurate is the scheme actually, and you can compare it against analytical solutions, for example. See how accurate you're solving it now numerically. Good. So you will have these slides. They will help you basically with the schemes. I will give you a template code. Can I show you that? Let me try to show you quickly the files. So I will put this homework 1 folder onto GitHub. So you can again just git pull the material. You will have the slides, basically that's the slides I just showed you. The slideshow, the homework that explains what your homework will be. And then I have you these 2 templates. One is in Fortran, another in MATLAB. Choose which one you like. If you want, you just rewrite in with Python and do it in Python or another language you prefer. So the code is very short, but it basically, the template sets you up already, gives you here the analytical solution, sets up the meshing, and then somewhere you will see the to-do. Do you see that? Okay, the to-do part is your part. So here it's asking you now to implement the scheme, for example. So implement your, for example, the explicit scheme. Forward difference in time, central difference in space. Put it here. Or the implicit scheme. Think about how to solve that. How to put these 2 matrices or the matrix form together. And then how to solve it with these matrices. Or the Crank-Nicholson scheme, for example. So that's your to-do part, basically. The rest, again, is basically already given here. It will just output you the temperature field, compare it against the analytical solution. It gives you every now and a snapshot of the temperature field, which you can then plot, for example. Here it already plots it as a PDF, for example, the figures. So you have this little template code in MATLAB. You have the same for Fortran. It sets up your mesh, your parameters, and then somewhere you have the time factor you can play with. And again, this to-do section where you implement the scheme, basically. So if you use these templates, there's not much coding you have to do. It's mostly really within just the scheme itself that you implement. And then you can start playing around with these time step sizes. Good. Let me quickly show you the homework PDF, if I can here. So that's also in this folder. Basically gives you what the problem set is, starts showing you these finite difference schemes. Again, goes through the heat equation, ending up, for example, with this very simple equation that you can use when we have a constant thermal diffusivity. And then it gives you the problem set, how you would set out the length, the problem, and then you start with an initial temperature distribution, and then see how that distribution evolves over time. And you use different time steps. That's basically the main homework. Try and put the scheme in place, the code, and then play with these time steps. So if you're brave, there are these extra questions you can play with. You don't have to. Start with this one, the first problem. Then if you feel brave and don't have too much headaches, just try and look into these explicit versus implicit schemes. So here you play with a bit different scheme. You will end up with a problem set up like this in matrix form, which you can solve as well. And if you're extra brave, then you can try and look into the Craig-Nicholson scheme, trying to implement that one as well. And if you want, for example, look at the accuracy of the scheme. The main point here is explicit versus implicit leads us into the stability of schemes. So that's why it's a nice example, where you start seeing that when we solve it numerically, the stability of the scheme, it becomes important. And if you look, for example, at the Craig-Nicholson scheme, it's a very popular scheme. You can also look, for example, how accurate is actually the scheme. So we saw this with the first order and second order truncation errors. So that gives you, that leads you into the accuracy of a scheme, for example. So you can play with these, and that's it, basically. So try by next Thursday to have at least this first one solved. If you want, you go on with the extra questions. Try to look at an implicit scheme and the Craig-Nicholson scheme. Good. That's it. So in terms of coding, there shouldn't be too much coding. If you use the Fortran or MATLAB scripts, it's really basically one line, not much more. And then you can play with the time step sizes a bit. And if you are feeling extra brave, look into the implicit scheme, how to solve that. Look into the Craig-Nicholson scheme, how to solve that. You don't have to, but if you want, you can do that. And the rest for the parallelization, I put you the solution into the Dropbox folder, and you will have then some more feedback, direct feedback when I look through your report. Is it good? Then we are all done for today. Brave, we have now 3 conservation laws looked at: mass, linear momentum, and energy. I found this energy is the most complicated one. But at the end, when we come to the heat equation or heat diffusion equation and the wave propagation equation, they look very simple. We only have these first, second order derivatives, which look a bit different between the two equations. The rest is exactly the same. But it's interesting to see then how much that changes the character of the solution. How a first order time derivative gives you a diffusion, and as soon as you have a second order time derivative, it gives you a vibration, basically. So the character of your solution changes completely by just increasing the order, the time order of the scheme. Good.